All right. A couple of things right from the start. First off, happy International Lego Day. Legos were patented back in 1958 on this day, and now have cost me a lot of money. Okay. All right. Second thing, some of you are currently scheduled in math support in our support area, and that is cool. That's awesome. Great. If there is a change that needs to happen with that because your schedules got all redefined yesterday at Conflict Res, if you need to change that, that's fine. No problem with that. You just need to email me now with what you want to be changed, or I need to move these mods. Can you find 2 other mods for me, or something along those lines, okay? On the column, kind of the second one down in between the 2 unit circles, is when we are in the MRC time. Those times haven't changed for us. There was another one around the room somewhere too, but I don't know where that one went. There it is. It's kind of underneath Tokyo. Okay. So those didn't change because Mr. Schmelling's and my schedule didn't change the second semester. Okay. Additionally to that, I'm gonna redo that schedule. Additionally to that, I'm also gonna put in times when I'm in support because I'm in support a lot too. And by all means, come into support and get that. We want to be available to you at all times. Whenever you're off, we want to be somebody available. Okay? All right. Lastly, we were talking about this yesterday when we were sitting at Conflict Res and we had a lull in our lines. First semester was kind of a warm-up. Okay? So we scraped together 16 questions for your final off of the NTC final. There are 20 more, and the 20 that are left to go in this semester are a lot. How do I want to say this? The difficulty rating, if you will, of those is a little different than the ones that you just saw. Okay? The ones that you just saw really didn't have very much. You didn't have to show a lot of work on that final. And you guys all just took it. Okay? You didn't have to show a lot of work on that final. Questions were a little difficult, but you didn't have to show much work on it. Second semester is all kinds of work that you got to show. Okay? We're gonna fill pages second semester with some problems. Okay? Just so you know. And I don't say that to scare you. I don't say that to be intimidating or anything. I say that literally because it is fun math. Second semester pre-calc is fun math because a lot of it is applications. We're going to get into navigation. We're going to get into launching an object. We're going to get into polar and parametric. We're going to do imaginary numbers, but in a different way. That's going to be so much easier than how you learned it on the other side of the wall last year. So yeah, it's fun. It's fun math. Second semester is fun math. Okay? All right? So, with that being said, in the immortal words of Jay-Z, please allow me to reintroduce myself, and we're going to talk the law of sines today. Okay? Now, when you were in geometry, because all of you were in geometry at one point in time, you learned about the law of sines. Okay? Hopefully you memorized it then. If not, we're going to show it to you here in the next slide. Okay? But we're going to take it up a notch. I don't remember if it's Emeril Lagasse who on his cooking show always kicks it up a notch, or if it's Guy Fieri. It's one of those like TV chefs that always like we're gonna kick it up a notch, and then they throw in a bunch more spices or something like that, and they make a big flame, presentation, all that fun stuff. That's what we're gonna do with the law of sines. Okay, so let's get into it. Okay, you can draw any triangle that you want because the law of sines works on any triangle. It doesn't have to be a right triangle. It doesn't have to be an obtuse triangle. It doesn't have to be an acute triangle. It works on any triangle that you want. Now, when we're labeling that triangle, okay, we label the angles with capital letters. So if I say that this is angle A, and this is angle B, and this is angle C, I would label those angles, those vertices, a vertex, vertices, okay? And I label those vertices with capital letters. Okay? Then the sides are lowercase letters, and it's opposite sides with the same letter. So if angle A is down here in the corner, left lower corner, then this side is side A. This would be side B. This would be side C. Okay? Vertices, capital letters, sides, lowercase letters. And it doesn't matter what combination you put those in. That's what I did. We could have gone and if that's the case, then this would be side C, this would be side A, and this would be side B. Okay? With me on that? Okay? It doesn't matter which order you put them in, just so long as... I like the pink ones better. Come on. Okay. Yeah? Just so long as opposite sides are same letters. Okay? With me? Okay. Anybody remember the area of a triangle? 1/2 base times height. So the area of a triangle is 1/2 the base times the height. Okay? Well, I know in this particular labeling of the triangle that side C, this right here, would be my base. Agree with me on that? Okay. I just need to find this height. Well, depending upon which triangle I want to use. If I want to use my left right triangle, or if I want to use my right triangle. Okay, which one, left or right? Left, okay. So if I'm going to use my left right triangle, I know that that is angle A. And I know that the sine of angle A is side H over side B from SOHCAHTOA. Sine of an angle is the opposite side, which is side H, or length H, I should say, over hypotenuse, which in this case would be side B. With me on that. If I manipulate this equation, multiply both sides by B, I get B times the sine of A is equal to H. Now, just for colorful sakes, I'm going to change this from green. It's literally going to be the same thing. Promise. But for colorful sakes, I'm going to change it from green to purple. Because now, when I go to my green area formula, the area of this triangle is 1/2 times the base. Well, the base is side C. And the height is B times the sine of A. Come on. With me? And so that's how we would get this one right there. Okay? And we could do the same thing over and over and over again, all on the same triangle, and get the other two. Okay? So all three of those represent the area of that triangle. Yes? Okay? So if all three of those represent the area of the triangle, then what? we know about all three of those then? If they all represent the area of the triangle. They're all the same, so that means that they're all equal. So let's set them all equal to each other. We had 1/2 A times B times the sine of angle C. We had 1/2 B times C times the sine of angle A. And we had 1/2 A times C times the sine of angle B. Actually, hold on. Let me change those around. Let me switch this one. Oops, I guess they're all locked in. Just for the sake of what's coming up. I should have put sine of B there. It really doesn't matter because we started with the sine of A anyway, so. But OCD kicks in from time to time. Okay? What can we do to that mathematical equation? We can multiply everything by 2. I would concur. We can multiply this one by 2. We can multiply this one by 2. And we can multiply that one by 2. As long as we do the same thing in every single spot, we're good. So then this would become AB sine of C, AC sine of B, BC sine of A. Yeah? Now, this one you might not get because it's not necessarily the easiest one to see, but now I'm going to divide every term by ABC. Again, mathematically legal because I'm doing it in all three spots. If I divide the first one by ABC, can I simplify it at all? A and B cross out here, A and B cross out there. Second one, A and C cross out. A crosses out A, C crosses out C, there's gone. Third one, B and C cross each other out. So that leaves me with the sine of angle C divided by side C is equal to the sine of angle B divided by side B is equal to the sine of angle A divided by side A. And that, ladies and gentlemen, is the law of sines. We will also refer to it as LOS. Okay? The sine of an angle divided by its opposite side, that ratio is equal on all three parts of the triangle, or all three vertices of the triangle. Okay? It's up there still, same thing. Okay? Law of sines says that the sine of angles is proportional to the side lengths of any triangle. Yes, that's what I just said. Side note, this is kind of important right here. To use the law of sines, we must have one complete fraction. You have to have an angle and its opposite sides. You have to have one of those sets. Okay? All right? The other thing that I will tell you also is that the law of sines only finds acute angles. Because if you remember back to first semester, when we were dealing with inverse sine, that only worked in quadrants 1 and 4. Inverse sine only worked right half of the unit circle. So that only would give us an acute angle. Okay? Law of cosines, which we'll get to probably next week, law of cosines will work for obtuse angles. Okay? Which also reminds me to tell you something that you should have learned in geometry, and you probably have forgotten. I'm hoping that you actually know the answers to this. I'm hoping you prove me wrong. In a triangle, the biggest angle is opposite what? The biggest side. Yep. Okay, biggest angle is opposite the biggest side. Smallest angle is opposite the smallest side. Okay? Okay? So that's how you know. So when you're finding the law of sines, or when you're using the law of sines, you want to go after the smallest angle available. Okay? Because you'll already have one. You need to get two more. You want to go after the smallest one, because the smallest one then is going to be acute. Because you can't have two obtuse angles in a triangle. Okay? Alright? Love it. So, you can just draw a regular old triangle. It doesn't have to look like this. It doesn't, I mean, truth be told, pictures are just pictures. We will never ask you to draw an accurate rendering of a triangle. Okay? In law of sines, law of cosines. Okay? If you wanted to make one of these angles be 104 degrees, that's fine. Okay? Right? That's fine. Okay? So, it says that we have angle A here is 48 degrees. And angle A could go in any of the three spots for you. I'm just putting it down there. Angle C here is 62 degrees. Side A is 16, which would be opposite of angle A. That leaves this side here being side C. That leaves this angle here to be angle B, and that leaves that side down there to be side B. With me on all of that. Okay? It is asking us to flat out do something that's called solve the triangle. Solving the triangle means you need to find all three sides and all three angles. Which means, in a solving the triangle case, how many answers do you have to get? 6. We give you 3 of them. You have to get the other 3, but you have to write down at the end all 6. Okay? Alright? So, if we're given 2 angles in a triangle, we know the third angle, because the third angle is going, there's 180 total degrees in a triangle. Subtract off the other 2, gets us the third angle. So 180 minus 48 is 132. 132 minus 62 is 70. Yeah? Yeah? 70? Okay. 70. Just as a side note, yes. The question was, do we have to write that work down? Yes, because we're a show work kind of class. Side note, you do not have to have one of our calculators, one of the graphers, to do this. Okay? If you do use one of ours, make sure it's in degrees, not in radians. Because law of sines, law of cosines will all be degrees. Okay? Right? Truth be told, it's easiest to do it on there because you can store stuff on there. I get it. Okay? But you have your regular TI-30, whatever calculator-ish it is, you can use that too. Okay? 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 So now that we have the third angle identified, we can set up the law of sine. The sine of A over side A, so the sine of 48 degrees over 16, is equal to the sine of angle B over side B, we don't know side B yet, is equal to the sine of angle C over side C. We don't know what side C is. So what we're going to do then is we're going to break this up into two different problems. The first problem that we're going to break it up into is going to be the sine of 48 degrees over 16 is equal to the sine of 70 degrees over side B. Now, the question was just asked, do we have to show our work? And yes, and here's why it's very important to show your work. Because sometimes you hit the wrong button on your calculator. It happens. I do it too. Okay? And if you have all of your work shown, then you can easily recreate what it was that you were just had that number on your calculator. Okay? With me? So I'm going to show all my work here. I'm going to cross multiply because I've got two equivalent fractions. So that's going to be B sine of 48 degrees is equal to 16 sine of 70 degrees. So then B is going to be 16 sines of 70 degrees all over the sine of 48 degrees. And now we can go to a calculator, making sure it's in degrees, and we can type that in. For me, come on, there we go. For me, it's going to look like 16 sines of, oops, I'm in radians, okay. 16 sine of 70 degrees. I'm going to put my degree symbol in there because if you're using our calculators, if you put the degree symbol in, it overrides the fact that I'm in radians already. All over the sine of 48 degrees. And when we calculate that, we get 20.231, actually, we get 20.231698. 231698. 231698. Hold on. I'm getting there. I got 231698. 2231,698. We will stay with our rounding to 3 decimal places going forward in second semester. However, I will tell you this. On the graphers, you can store that value exactly in your calculator. Okay? Right? On TIs, you can't. So I would write this out as long as you can, okay? Because if you have to use it, then it is. When the answer keys happen, we go off of exact stuff. Like we just store and we just keep going, okay? All right? So in this particular case, we don't have to use it again, but just know that if we would have to get a few more decimals in there, okay? My second fraction then is going to be the sine of 48 degrees all over 16 is going to equal the sine of 62 degrees all over C. I've got to do it all over again. I can't use the Pythagorean theorem because it's not a right triangle. So I've got to do the law of sines twice. Okay? So then that gives me C sine of 48 degrees equals 16 sine of 62 degrees. So that gives me C is equal to 16 sine of 62 degrees all over the sine of 48 degrees. And then that would be C equals B down there, 62, 48, clear, up, enter, here, delete, 62 there. Oops. And then up and 19.009971. 19.009971, right? Is that what I said? Come on. 009971. Yep. Okay. So in the end, my answers are going to be angle A was 48 degrees. Angle B was 70 degrees. Angle C was 62 degrees. Side A was 16. Side B was 20.232. Side C was 19.010. And those are the 6 answers that we need to give. Even though we were given 3 of them, we still have to give all 6. We have to solve the triangle. Questions, comments, concerns, clarifications? You want to try this one on your own, or do you want us to go through it together? Own? All right, go for it. Solve me the triangle. So that's 85, so that's 95, so that's 94.30. $111, $118, $118.40. No, it should be 20. Sorry. Oh no, this one should be 20. That's where. This one was 61 degrees, 20 minutes. Yep. 30 minutes. Yep. Yep. Agree or not? We got here.
Is it the same as 95.5?
Oh, wait. Were we not supposed to convert the minutes into degrees?
We already are in degrees. Yeah. Yeah. We can use it as degrees of minutes because how many minutes are in a degree? 60. So 10 plus 20 plus 30 gets me 60, so there's 1 degree.
Oh.
Yep. And then we don't have to worry about fractions.
Okay, so I didn't
Yeah.
have a calculator.
Yep. Yep.
Oh, you type that in the calculator.
You should have a degree minutes. Right there. Okay. So then we've got the sine of 24 degrees 10 minutes all over 4 equals the sine of 61 degrees 20 minutes all over side C. Oops. So then C here is going to be 4 sines of 61 degrees 20 minutes all over the sine of 24 degrees 10 minutes. Glasses might be a good thing. For sine of 61 degrees 20 minutes divided by the sine of 24 degrees 10 minutes gets me 8.572954. Okay. Then we would have the sine of 24 degrees 10 minutes divided by 4 is equal to the sine of 94 degrees 30 minutes all over, this is side A. Yep. Yeah? What's up?
How do you put minutes in your calculator?
On that one,
Yeah.
there's a key right up here at the top. Let me see this for a second. Right underneath your DEL key that looks like a degree, minutes, and seconds key.
How do you do that on?
Probably under angle. Yellow on pink is not. Give me a second to finish it off, and then I'll find it. I know it's on there.
There's no judgment.
None. So this would be A here, would be 4 sines of 94 degrees 30 minutes all over sine of 24 degrees 10 minutes. I get 9.74 04597. I was trying to get to a good rounding spot and look ahead. Okay, so that would be side A. Then would be 9.740, and side C would be 8.573. Okay, if you convert it to decimal degree or from degrees, minutes, seconds to decimal degrees, that's fine. Just know that these conversions, because it would have been 24 and 1/6, and that 1/6 is not a nice decimal, so you got to keep it in fraction form. Okay. Same with 61 and 1/3 it would be. So you would have to go 0.3 repeating, which even if you go 0.33, that's still not the same as 1/3. Okay. And so you're going to be off. And the more that you're off early, the more, if you're off early in the problem, the more you're going to be off late in the problem. Okay? Because you're going to use that on top of things. Okay? Go for it.
Started the day off with the law of science.
Great day, isn't it?
That's why I got one.
Okay? We can use the law of sines because we have a complete fraction. Okay, we've got side A and angle A. So then we would first off hammer out the sine of 32 degrees over 17 is equal to the sine of angle B over 11. So then that's going to be 17 sines of angle B is 11 sines of 32 degrees. That's going to be the sine of angle B is 11 sines of 32 degrees divided by 17. So angle B here is going to be the inverse sine of that. So when we go to type that in the calculator then, oops, what's up?
How come we're using inverse sine?
Because we have to find an angle.
Oh, okay.
Okay? So, oops, just copy out of that. So we would say we want the inverse, whoa, tap the brakes here, come on. Inverse sine of, what was it again? 11 sines of 32 over 17. Now, that to me, in mine, that's giving it to me in radians, so I've got to multiply that by 180 and divide that by pi, convert it out of it. So that gives me 20.053 for the angle. Okay? Now, I'm going to have to use that again, so I'm going to leave it on my calculator as is. For me, I am going to store it as angle B. Okay? So now it is stored in my calculator for all of the times as angle B, or as letter B. Okay? What do we say? 20.053. And that's in degrees. Now we can say that angle C is 180 degrees minus 32 degrees minus angle B, which I'm stored in my calculator. Oops, get off of there. Oops, get off there. Okay. So now when I go to my calculator, now I can go 180 minus 32 minus, now all of your calculators have the ANS key on it. That's the last answer that it gave you. You could do minus answer for that one. For me, I'm just going to go minus B. And that gives me that angle C here is 127.947 degrees. And now I'm going to store that in my calculator as angle C. 127.947. Because now I have to go the sine of 32 degrees all over 17 is equal to the sine of angle C over side C. So side C here is 17 sines of 127.947 degrees divided by the sine of 32 degrees. $17, right? Yep, 17. Trig sine of C
I really want to show the way.
degrees divided by the sine of 32. And that would give me 25.298. Angle A is 32. Oops. Angle B was 20.053 degrees. Angle C was 127.947 degrees. Side A was 17. Side B was 11. Side C was 25.298. Boom.